various collaborators over the last 2 years. The people who were involved were Ferenc Balog, Jacques Urtubise, and Sasha Orlov. And it concerned, well, at first it concerned relating KP tau functions to BKP tau functions. But as a spin-off, it was actually a little bit of a spin-off of the book, which I hope you all have seen, on tau functions and their applications. As a spin-off, we found an identity which somehow can be dug out of Élie Carton's book on spinors, but not in this form, which is just a very nice identity, which I think everyone should know, that allows us to expand the determinant of a skew symmetric matrix, or at least the determinant of minors, principal minors, or not even principal, off-diagonal minors, as a sum over products of Pfaffians of the principal minors. In other words, all of the minor determinants of a skew symmetric matrix are uniquely determined by the principal minors of the corresponding Pfaffians in a bilinear manner. And this has a deep geometric meaning in terms of spinors and Grassmannians and orthogonal, I mean, isotropic with respect to a quadratic form orthogonal Grassmannians. And then we realized that this actually generalized a lot of results that were known about Schur functions and Q-Schur functions, and in fact extended to characterize relations between general lattices, Schur lattices of KP tau functions and BKP tau functions. The main tool is Fermions, so I hope that people are okay with that. And I'm just going to go ahead with this. It's going to be pretty elementary because I'm going to try to make everything explicit. So here's the outline. I'll recall what BKP and KP tau functions are. I think everyone here knows, and the special role played by the Schur functions and the Schur Q functions. Then I'll just recall the usual conventions about partitions, Young diagrams, and so on. And then write down a couple of examples of such determinantal Pfaffian bilinear expansions. You should look at these as sort of hybrid. There's quite a few of these hybrid determinantal Pfaffian analogs of things like the Cauchy-Binet identity. And then finally, using the fermionic representation, I will show how you can construct lattices of tau functions, of which the Schur functions and Q-Schur functions are special cases, but they're all labeled either by partitions lambda or by strict partitions alpha, just like the S and Q functions are. But these are lattices of KP and BKP tau function. And finally, the general formula, which allows us to expand such lattices of KP tau functions in terms of bilinear sums over products of, this should be function here, of BKP tau functions. And if there's time, I don't know, I'll try to give some examples. Okay, so here's the standard definition. Everyone knows this. Here's the Hirota bilinear relation for a KP tau function. I'm not going to explain the notations. Some people have already explained it in earlier talks. I think that this is well known. So T is the infinite sequence of KP flow variables. The Z inverse square is a abbreviated notation introduced by Sato. You translate the T by Z inverse in the plus and the minus direction. You take another parameter, which is sometimes called S. Here it's T minus delta T. You write down this formal residue relation, which means that the 1 over Z coefficient in the formal expansion of this product is equal to 0, and that gives you identically, that's identically in both in the delta T variables, that gives you the infinite hierarchy of KP KP hierarchy equations, of which the first is the KP equation itself, where U is the second logarithmic derivative of the tau function. Okay, so that's standard, and similarly, very similarly, we have the BKP Hirota bilinear relation. In this case, only the even flow variables, only the odd flow variables T1, T3, T5 enter, and it's very similar, but there's a right-hand side, it's still homogeneous and quadratic. And that is equivalent to the hierarchy of BKP equations. And here, using the Sato notation, this is the bilinear form of one of the top elements of the hierarchy. So the notation being used, boldface T is this infinite sequence of KP flow variables. Boldface T with a B is every second one of these. And so this is also notation. When you put a bracket around X, that means the normalized power sums. So you can either view the X's as the independent variables or the T flow variables, which are normalized power sums. This is all very standard. And so we think of the Schur functions and the Q Schur functions as either functions of the finite or infinite set, symmetric functions, or symmetric polynomials if there's a finite set in these X variables, or as polynomials, graded homogeneous polynomials in the T variables. And just to recall, a partition is just a weakly decreasing infinite sequence of integers which eventually saturates at 0. And the point at which it saturates at 0, the number of non-zero ones is called the length, and the sum of the lambdas is called the weight. And it's usually represented by a Young diagram. I think everyone knows this, where the rows are the number of parts of the partition. Another representation is using the so-called Probinous Indices, which is entirely equivalent to the partition. You look at the arm length and the leg lengths along the diagonal, and this set of pairs of numbers, alpha 1 to alpha r, beta 1 to beta r, contain exactly the same information as the partition. You can translate from one into the other, and with very simple formulas. And r is the number of diagonal elements, and that's called the Provinious degree. So just to recall the formula for Schur functions in terms of the X variables, it's given by this formula, which is due to Jacobi. It's the Jacobi bi-alternate formula, but it actually is a special case of the Weil character formula. So it's a determinant. There are many determinantal expressions for the Schur function, but the important thing to remember is that the Schur function is, when viewed as a function of the T's, is a KP tau function and the basic building block for all KP tau functions. Similarly, we can define the Schur Q functions, which play a similar role with respect to projective representations as the Schur functions do with respect to ordinary representations. And in this case, I'm doing it using a generating function to generate the elementary Q Schur functions, then forming a matrix Qij as bilinears in the elementary ones. This is very similar to the Giambelli way of expressing the Schur functions, and then forming a Pathian. This is a skew-symmetric matrix. All of this is in McDonald's book. This is a skew-symmetric matrix. The alphas are distinct, and so the Pathian formed from this Q is what defines the Q Schur function as Schur originally defined it. There are other ways to do it. And the main thing is that these are the building blocks from which all KP and BKP tau functions are formed as linear combinations. At least formally, every KP tau function is a linear combination of Schur functions with coefficients pi lambda that satisfy the Plücker relations. These pi lambdas should be interpreted as Plücker coordinates of some element of an infinite Grassmannian. Very similarly, the KP tau functions are linear combinations of the Q Schur functions with of course, the Plücker coordinates are determinants. They're determinants of minors of some infinite affine coordinate matrix. And these are Pathians. They're Pathians of a suitable matrix. And what they really represent, just like the KP tau function, the Plücker coordinates represent a point in an infinite Grassmannian. A BKP tau function represents a point in an infinite isotropic Grassmannian with respect to a quadratic form, with respect to which it is maximal isotropic. And just to recall, this is formal stuff, but we have the Plücker relations, which are standard, which define essentially a decomposable element under the Brooker map, the Grassmannians get mapped into the exterior space formed from the underlying vector space, and the fact that they're decomposable is contained. That is the equivalence of the Brooker relations. And very similarly, we have what I call the Cathode Relations, which are bilinear expressions for the Cathode coefficients, which is the expansion coefficients of an isotropic Grassmannian, also embedded into projectivization of the exterior space. So these two relations are completely equivalent to the Hirota bilinear equation. They're an algebraic way to write down an infinite set of bilinear constant coefficient differential equations. Okay, now a little bit of notation. So now I'm going to give you an identity, which should be actually well known, but doesn't seem to have appeared previously in the literature explicitly, except in a very implicit form in Carton's book. So suppose that A is a skew n by n matrix, and we take subsets ij of the indices, so subsets of length r of the indices 1 to n, and we form the R by R, not necessarily diagonal minor. So this is just any minor of this skew matrix. Now there's a notion that I have to introduce to make this identity concise, and that is the notion of a polarization. So a polarization is some other way to split things up. So you have I and j given, and we're going to talk about a polarization of a pair ij. This will be another pair, KL, not necessarily of the same length. These are the equal lengths R. These are other lengths, not necessarily, we'll call the length K and the length L, but they are the same elements. That is, the union of K and L is the same as the union of I and J, and the intersection is the same. That's what we call a polarization. And the number of common elements we call S. So this is just notation to make it easy to write down the formula. Now it's an elementary combinatorial exercise to check that the number of polarizations is given by 2 to the 2r minus 2s. And now we can add a little bit of information which distinguishes in an enumerative way all of these distinct polarizations. We call this a binary marking. So a binary marking for a sequence of 2r integers, like the k and l and the I and j, is an assignment of signs, plus or minus sign to each of them,
Sorry,
giving
John,
a sequence
can I
of
interrupt?
k. Yes.
Can you go back to the definition of polarization, please? That went by too fast.
Okay. So polarization is another pair KL of integers from the same set as I and j. In fact, their union is the same.
You said you wrote I union j is 1 through n. Is that
Okay, I knew you'd ask that. I knew somebody would ask that. This is not essential, okay? So what is essential is that the identity that I'm going to write down will only refer to the n by n block. So if n happens to be a bit bigger than I union j, then you just ignore the other ones and just take the ones that are in that block. Okay, so this is sort of an auxiliary simplifying. It's not the essential thing. The point is that the identity only concerns those n-tuples which are inside of an n by n block. That's all this means.
Sure.
But if you, in the original paper, this condition is not required, but we just look at the subset. Is that okay?
Yes.
Okay, but the crucial thing is that the union of K and L and the intersection of K and L is the same as the union of I and J and the intersection of I and J. That's what the essential condition is. The question you just asked was exactly the same as what Marco asked in the previous seminar, so I understand the concern. You can ignore that and just say we're talking about a smaller number n. Okay, so the markings, as I say, are a set of signs that are attached to this sequence, which, so it's a refinement. And that makes it, if you do the counting, it makes it a one-to-one correspondence with the various, well, with what we're going to now identify. So we have to define a sign of a pair KL, and the sign, if you choose your signs epsilon, to be the unique ones, the unique binary markings, such that if I, M, and Jn are equal, then the first one gets the sign plus and the second gets the sign minus. Otherwise, no constraints because they're distinct and you could have either plus or minus going either. But impose this constraint and it makes it a one-to-one correspondence. So now we only take okay, we're going to use these signs to define a sign of KL as being the sign of the permutation K plus L minus, because now this is a permutation of this. There's no zero there. That's supposed to be times, okay, sorry, this is supposed to be the element which is marked with pluses on the left and minuses on the right. So that defines the sign of the polarization. There's also some cardinalities, which are the intersections of I and K and I and L, and the sum of these two, it's easy to see, is equal to R, the number of elements in I and J, and S, the number of elements in their intersection. So now I can state my identity. I have all the definitions necessary. Let's denote by KK and LL the principal minor submatrices of the skew matrix A with columns KK and rows LL. And now take an arbitrary minor, IJ. So if R by R, size R, then this identity holds, and it has a deep meaning in terms of spinors. The determinant of this minor is the sum with suitable signs defined above of the products of the principal Pfaffian minors. So you take the Pfaffians of the principal minors, KK, LL, summed over all distinct polarizations. Okay, that's a bit of a mouthful, but it's not really complicated, and it's easy in any example to write down what, I mean, we know how many terms there are in the sum and so on. So this identity doesn't seem to be well known, and it's not in Carton's book explicitly, but if you read very carefully his theory of pure spinors, you'll see that this is a consequence of some of the things that he says. Okay, here's a theorem now. This is an abstract identity for matrices. Now I'm going to concretize that and give some functional realizations of the same identity, where all the matrices are particular functions, and in general, they're going to be tau functions. But let's start out with the building block tau functions. So let's call T primed every T primed is T with every second flow variable set equal to 0. Okay, that's not to be confused with TB, in which the zeros are just absent. Here they're present, but they're equal to 0. And this is the Probinous notation for the partition. Then this identity, which I wrote down in abstract in the previous transparency, has a particular realization in terms of Schur functions and Q-Schur functions. Remember that Schur functions are determinants and Q-Schur functions are Pfaffians. So this is a model realization of that previous purely linear algebraic identity or matrix identity of the that we wrote down before. So the left-hand side has become the determinant of some Schur functions, and the right-hand side products of determinants, products of Q-Schur functions. Okay, so I won't go through the details of this, but the P alpha here are all the polarizations. This is a slight shift. There's a little conventional thing here where you take a strict partition alpha, which starts with 1. It's between 1 and n. And then you take a shift of that thing by 1. So this is in MacDonald's book. It's just a question of notation. So that's what the polarization involves, this shift when you write it in terms of the Frobenius indices. Okay, something also from MacDonald's book, there's something called a double, where in terms of Frobenius indices, the first part is the same as the second part minus 1 in every part. That's called a double. And that gives me a chance to cite an example of the previous identity. The Schur function for a double, so alpha is a pure partition and d of alpha is its double, This identity, by the way, can be found in McDonald's book. This is a very special case of the previous identity. It's equal to the square of the Q Schur function for alpha with 1/2 t, if it's even, and similarly if it's odd. So that's the first example that can be found in McDonald's book. Here's a second example. Suppose we have a hook partition. So that means the Probinus indices, the Probinus rank is 1, and there's just one arm and one leg. In that case, the number of partitions is 4, and the number of polarizations is 4. Either we have A, B plus 1, or B plus 1A, or the null set with A, B plus 1, or A, B plus 1 with the null set. And that gives you the identity reduces to this relation for hooks. And this relation you can also find in McDonald's book. So two special cases of that Schur function identity can be found in McDonald's book, but not the general case. Now I'm going to derive this and a more general result using fermionic vacuum expectation values. So this is standard lore. It's Clifford algebra in infinite dimensions. We take some sort of Hilbert space, which is spanned by an orthonormal basis, Ej, separable Hilbert space, and its dual. This is just the algebraic dual with its basis. And we form the semi-infinite exterior product. And that is the fermionic Fock space. That's the module, the unique irreducible module of the underlying. I'll define what the Clifford algebra is in a moment, but basically it's the spinor module. The basis elements, this is very standard, I'm just reviewing this, are given by monomial exterior products in a sequence of basis elements that are strictly descending. And the relation between the indices and the partitions is this. This is a very standard thing. For those familiar with integrable systems, this is standard. These are the coefficients in the Maya diagram corresponding to a given partition and a given fermionic number n. In any case, there's a shift. Lambda is weakly decreasing, saturating at 0, whereas L is strictly decreasing, saturating at all subsequent negative integers. That's how we define the basis elements labeled by a partition in the nth vacuum sector. And the Fermi creation and annihilation operators are just exterior product with the basis elements or interior products with the dual basis elements. And this exactly realizes the Clifford algebra corresponding to a quadratic form, which is null on the H subspace, null on the H star subspace, and H and H star are dualized. And the basis elements in Frobenius notation can be written. This looks like a kind of construct. So this is like a maximal weight vector representation. But in fact, there's one sector for each integer n. These are called the fermionic charge. You act on this maximal weight vector, vacuum vector, by a finite number of bilinear combinations of creation and annihilation operators, the number being the Frobenius index, and well, this is another way to write the basis element. So in these terms, in terms of fermionic charge creation and annihilation operators, the Schur function. Well, let me go back a moment. Any tau function, any KP tau function has this universal expression, which goes way back to the late 1970s and Sato's work. You take a vacuum, this is n equals 0, vacuum expectation value. Here you have any GL infinity group element. Sorry, excuse me. Here you have any GL infinity group element. Here you have a polynomial in the creation and annihilation operators. And here we have the standard flow group for the KP dynamics. So G can be represented as the exponential of bilinears in the psi's. U are bilinears in creation and annihilation operators, and the so-called currents, which generate the abelian group gamma. These all commute, and they are also special bilinears, and this is the shift flow. This is exactly the dynamics on the Grassmannian. of the, or rather on the fermionic Fock space of the KP flows. So in particular, a Schur function is a KP tau function, and it's the one where the U term is just the identity. Sorry, the U term is just the product of the psi daggers. The G term is absent, and that's it. I mean, this is the fermionic representation of Schur functions. Now we have a similar thing for Q for BKP tau functions and Q Schur functions. I'm not going to go through the details, but basically we take a subspace amongst the spaces involved. These are spanned by linear elements, which are called neutral fermions, and they're these linear combinations. There are two types: psi j plus a certain sign times psi dagger minus j, or minus the same thing. These two commute. They don't see each other. They're independent, and they satisfy these Clifford relations. This goes back to early 1980s, the Statoil school. So we define two spaces. We'll need actually both of these. Two spaces, the plus space and the minus space, which are both subspaces of the fermionic Fock space, which are invariant under these respective groups that are generated by these plus and minus operators. So here we use a refined basis, the plus basis, consisting of the vacuum. Whoops. What's that? Okay. The plus basis consisting of the vacuum acted upon by all of these plus creation operators, neutral operators, and the minus basis for the minus states. We have a quadratic form, which was the underlying quadratic form we were using before to define the Clifford algebra, where, well, this is it. I mean, it's the natural pairing of the Hilbert space H with its dual H star. So it defines an off-diagonal quadratic form, and the underlying Clifford algebra is with respect to that quadratic form. And in this, in the direct sum of H plus H star, we have two mutually orthogonal subspaces, H tilde plus and H tilde minus. Okay, so the analog of the KP tau function is this BKP tau function. I'll get back to the polarizations in a moment, and that is given by a similar formula. Okay, sorry. Yeah, that's given by a similar formula where we have the, sorry. No, I have to go back to the general definition here. Here's the general definition of the BKP tau function. Anything that satisfies the BKP Hirota equations can be represented fermionically like this, and this is a Pfaffian. So here we have again some polynomial elements U in the Fermi creation and annihilation operators. We have a group element H. These two are the plus and minus signs here are completely independent of each other. So we have two different classes. In fact, the same tau function could be defined either with the plus or the minus neutral Fermi operators. And this is the vacuum expectation value. It's very similar, but the flow group here only contains every odd flow variable as usual. In particular, the Q Schur function has this representation. So it's a very special case of this, where the H is absent and the U's are products of phi's. So that's the Fermi representation of the Q Schur functions. And in general, for any group element G, we can associate a lattice of KP tau functions. Notice what's happening here. Instead of having a vacuum here, we have one of the basis elements. So the lattice, I mean, the lambda and alpha beta are just different notations for the same partition. And instead of taking the vacuum expectation value, which defines the original KP tau function, we make a lattice of these things by introducing these polynomial elements on the right, and specifically choosing the Fermi creation annihilation operators corresponding to a basis element, lambda. So that gives you a lattice, a Schur lattice of KP tau functions, labeled by partitions. Similarly, we define a lattice of BKP Tau functions by replacing the vacuum element here by the basis that I defined before, obtained from applying the neutral fermions to the vacuum, and where the alphas here are strict partitions. So a standard result, which goes back to 1980, is the fact that if you take any BKP Tau function, Tau H BKP, and square it, remembering that TB are just the odd flow variables, you replace that by a sequence T prime, which is the same variables with zeros interlaced, and that is a KP Tau function. That's a well-known result. So this relating BKP with KP. So the main result that I'm going to announce is a generalization of this, where instead of having just this KP Tau function and this BKP, we have this lattice of KP Tau functions and this lattice of BKP Tau functions, and it will be a sum over bilinear combinations of the lattices. So again, remember the polarization that we defined before. I don't want to redefine the notation. There's some cardinalities. Pi is a cardinality. If you read off the specific case of the identity, the determinantal identity, determinantal Pfaffian identity that we had at the very beginning, for this case, remembering that pi, this is the KP Tau function lattice, is a determinant, and kappa, that is the BKP Tau function, is also a lattice, you obtain this general formula. So this is the most general form of that identity in terms of functions. And these functions are not just Schur functions or Q Schur functions, but this lattice of KP Tau functions and BKP Tau functions. So I'm just repeating it here for you to look at. So here we have a lattice, specifically defined lattice of KP Tau functions labeled by partitions, and another lattice of BKP Tau functions labeled by strict partitions. We have this familiar bilinear expression and a sign that is determined by the polarization in the sum. So it's essentially the same formula, but now realized functionally in a variety of ways, because it depends which group element H and which group element G of H you have used. So this is actually an infinity of different identities, all functional realizations of that determinantal Pfaffian identity. Okay, this is a sketch of the proof, but I think in view of the time, I'm going to only display it without going. The proof comes down to something really quite trivial. It's the fact that the phi plus and phi minus neutral fermions commute. And that means that when you take a vacuum expectation value of a polynomial in one of these things multiplied by a polynomial in the other, it factorizes. That's the key step in the proof of the identity. The details are, I'll give you references. This is actually a summary of a sequence of papers. Okay, so here's some specific examples. Suppose we set the flow variables equal to all to 0. So there are no flow variables. There's no longer any t dependence. Then you get an algebraic identity, and sure enough, it's the one which we started with. We recover the original sort of Pfaffian determinantal analog of the Cauchy-Binet identity. Now let's do another choice. Suppose that we leave the t's, the flow variables, to be anything, but we choose the group element to be just the identity element. Well, remember that gave us the Schur functions and the Q Schur functions. So there's no surprise in the fact that the identity then reduces to the second expression, which was the functional form of the identity, relating Schur functions to bilinear sums over products of Q Schur functions. So that's just another case. Now, actually, I'm almost at the, and this is actually two talks stuck together, and I thought I'd be finished before reaching this point, but it seems that I still have 5 minutes left. So I'm going to just make a quick comment of one more spin-off of this analysis. And that is this fermionic representation of the Schur function lattices and the BKP, I mean, of the KP lattices and the BKP lattices, this fermionic representation in particular gives a very nice explicit determinantal Empathian representation of all polynomial KP tau functions and BKP tau functions by switching from the t variables, the flow variables, back to the x variables in which everything is a symmetric polynomial. So I'm not going to go through the details of this, but what the result is that the previous fermionic representations, I'll just remind you what they are, the fermionic representations of these two classes of lattices of KP tau functions, here's one of them for the KP, and here's the other one for the BKP. That this, if you replace the t's by, interpret the t's as normalized power sums of the x variables, as one does when talking about Schur functions. If you do that, and you impose a certain triangularity condition on G, an upper triangularity, and similarly on H, what you end up doing is picking out from the whole huge, vast Riemannian of tau functions, you pick out exactly the polynomial tau functions. And that is something that in a different representation was shown by Johann van der Leur and Victor Katz. So we rely on the completeness of this, on their results, but the representation follows from this fermionic calculation. So here's the result. So I'm not going to go through the details, but here's the result. We have a group element defined as associate. Okay, let's go back. So suppose that in this exponential, remember that G is the exponential, where is it? G. G, well, here it's H. H is the exponential of bilinears in the neutral fermions with coefficients of matrix AJK, and similarly, the group elements in GL infinity can be represented as an exponential of bilinear elements in creation and annihilation operators with a matrix coefficient. Now, the assumption is that this matrix, this infinite matrix, is upper triangular. That's the specialization. And if you do that, you get the following beautiful result, I think beautiful. You generalize two things. You generalize, here's one result. You generalize Jacobi's bi-alternate formula, which was the definition of the Schur function, to something more general. These are all KP tau functions. They're labeled as usual by the lattice of partitions. And what enters, this is a bi-alternate, it is the same Vandermonde determinant of the denominator, but we have a bi-alternate, so the numerator is also an alternate. But the polynomials that enter in the numerator are not the monomials, like in the Weil character formula. They are polynomials which are determined by the group element whose exponential is e to the a tilde. So that gives you a triangular matrix of coefficients of monomials normalized. They're monic polynomials. So monic polynomials of all degrees. And you substitute those polynomials into the bi-alternate formula of Jacobi. And sure enough, you get the polynomial representation of this lattice of KP tau functions. And by considerations in the papers by Johann and by Victor Katz, this exhausts all polynomial tau functions. But they don't have this actual representation, but they do have a proof of something equivalent to this, exhausting all. And similarly, this is the last transparency, I think. Similarly, there's a beautiful generalization of a formula due to NEMO, which expresses Q Schur functions as ratios of Pfaffians. And okay, I have to define everything here, but this would be NEMO's formula in the special case where V is 0. Let's see. M of X is just the standard Hilbert matrix, which looks like this, XA minus XB over XA plus XB. Sorry, the V is not 0, I'm sorry. In NEMO's formula, V is a set of columns of monomials. They're the monomials. Whereas in our case, these are polynomials. So it's not a homogeneous symmetric function, but it is a symmetric function. And so this is the generalization of NEMO's Pfaffian representation of Q Schur functions. The H's are constants which are obtained, I mean, I'm not going to go through the details, but the H is obtained by vacuum expectation values of bilinear products of the neutral fermions evaluated at the value A. So there's a specific formula for all of these. And so this is the general representation of all polynomial BKP Tau functions. And that's the end of my talk, I think. Oh, sorry, references. Here are the references. So you can look up Cartan's theory of spinors and McDonald for background information. And the sequence of papers that are summarized in this talk are, first of all, the algebraic paper with Balog and Utebis, and then the 3 Tau function papers jointly written with Sasha-Orla. Okay, thank you very much.
Thank you, John. And thank you for, for rescue the day. So we still have maybe a couple of minutes for questions, remarks.
So I have maybe a question. You mentioned this expansion of BKP Tau functions in terms of bilinears of KP Tau functions in terms of bilinears of BKP Tau functions. Could something similar be, is there something similar done along these lines for DKP Tau functions?
For DKP. In some sense, that's contained in this, because BKP and DKP, one can be viewed as a sort of a restriction of the other. So we didn't separately treat DKP, but you can extract the DKP results out of these BKP results. So this is fairly standard. It's in the can be seen from the papers by Johan and Victor Katz. So it's not that they're new identities, it's just restrictions over the ranges. I thought you were going to ask about CKP.
Ah, well, yeah. That.
Where my answer is I have not.
Okay.
More questions? So, John, thank you again very much. And as I understand, as I see Mark and Gaetan are back, so you fixed Gaetan problem?